Okay, so I guess let's start now. All right. So we're very happy to have Victor here today to tell us something about the Virasoro minimal strings and 2D string cosmology. Okay, all yours now.
Okay, well, thank you very much. Thanks again for the invitation. It's a pleasure to visit virtually, at least Virginia Tech, and meet all of you. And so today I'll talk about mostly about this latest paper based on work with collaborators Scott Coley, Lawrence Eberhard, and Beatrix Muhlmann, as well as two other papers I wrote earlier last year as well. But that will be rather brief. It'll be a different another piece of the story that will come to it, and mostly be about two-dimensional strings. Okay, so let's get started. So, but before that, let me just again acknowledge my collaborators, Scott, Lawrence, and Beatrix. Okay, so with that, here's a brief outline of what we'll be discussing today. So first, I'll put things into context, a little intro into low-dimensional string theory, and as well as two-dimensional gravity, which are sort of the two concepts that we want to explore and try to merge in some way. So part one, which will be most of the talk, it will be about the quantum gravity point of view. So viewing the worldsheet as a quantum gravity model, and then I will describe what the theory is, Virasoro minimal string, what kind of string theory this is. And then I'll describe briefly some connection to 3D gravity, which sort of makes the connection a bit more clear to what is the proposed dual of this string theory, which is going to be in terms of the matrix integral, a matrix model. And the last part of the talk I'll describe what is target spacetime interpretation for this string theory. So the more conventional sort of way we think about strings. And the emphasis there would be that it's some sort of a cosmological model. Okay, so that's a brief brief plan. So let's begin. So first, just a couple of words. So just put things into context. What is low dimensional string theory? So they're, in a practical way, they're just theoretical laboratories for trying to understand fundamental aspects of string theory in the simplest possible context. So they're much simpler than their higher dimensional counterparts, like 10-dimensional superstrings, but nevertheless still retain some interesting phenomena that we hope to explore. So, for example, there's three things that still appear in low-dimensional string theory. For example, holographic duality. For instance, these two-dimensional strings are dual to matrix quantum mechanics, simple models. So they still exhibit this type of duality. Also stringy dualities, like T-duality and S-duality of that type. Another important example is non-perturbative effects, a certain class of them at least, D-instantons. These can also be studied in these low-dimensional models, and it's much simpler to do so in these ones than in, for example, the type 2B superstring, which is a lot harder. And finally, time-dependent phenomena, which it's a notoriously difficult subject in string theory, but still there are a few examples far and apart in which time-dependent phenomena can be seen even in these low-dimensional models. Okay. Nevertheless, it's still, string theory, even in this low-dimensional models, is still kind of difficult. It's a little bit of a messy thing to try to go and compute amplitudes in the usual sense. And we'll come back to this. Okay. So here are some examples of low-dimensional models. We have, for example, the sequel to one string is probably the simplest example, and this is dual to matrix quantum mechanics. A second example is just a supersymmetric version of it in the worldsheet. And sometimes it's called type 0A and it's type 0B. And it turned out these are also dual to the same matrix quantum mechanics. Other famous examples, of course, is, for example, 83 CFT2 strings, for which when there's no flux, then we do have a worldsheet theory for these. And another, perhaps even simpler, type of low-dimensional string theory is the minimal string, which you couple a minimal model in Liouville theory. And these, instead of being dual to a matrix quantum mechanics, is dual to a single matrix integral, as we'll have more to say in the next few slides. So in fact, this last type of example is the one that we're going to follow a little bit more closely, the minimal string. Okay. So before we get into details, let me just flash you what the model that we're going to be discussing today is. So the Virasoro minimal string is a new kind of example in this list that I presented in the previous slide. And the worldsheet theory, we can describe it exactly as in terms of conformal field theory, and these are the ingredients. So we got something that's called timelike Liouville CFT, which we'll describe more detail later. And then space-like Liouville CFT with center charge greater than or equal to 25. This is perhaps a familiar ingredient for this low-dimensional models, just the space-like Liouville CFT. And then coupled to the conformal ghosts. Just so, and you arrange it in such a way that the total central charge of each of the sum of all these ingredients adds up to 0. And we have a critical string theory in the usual sense. Okay, so that was just a preview. But before we get into it, let me just make a sort of a slightly philosophical point. Usually in string theory, in string perturbation theory, we have with this the main object of interest is the worldsheet CFT, which lives in some worldsheet here on the left hand side depicted with coordinates down sigma. And what you do is integrate over metrics to the metrics on the worldsheet and so on. But of course, the string theory is what we actually care about is how this worldsheet is embedded in spacetime on the right hand side. So how the string propagates in spacetime and traces out a 2 in this worldsheet, and we can compute scattering amplitudes and so on. Okay, but I think the first point of view we'll take is that actually we'll just care about the worldsheet CFT as a model of gravity itself. So suppose we don't care about the strings in spacetime. So we'll just consider the worldsheet theory as a model of quantum gravity in 2 dimensions. Okay, so it's a little bit of a philosophical point, but hopefully we'll, if you keep this in mind, we'll hopefully make things a little less obscure what we're talking about. Okay, so along these lines of models of 2D gravity, has been some very recent work on and a surge of interest in nearly pure theories of 2D gravity. By nearly pure is like I just mean that it's mostly a theory of just the Einstein-Hilbert term. For example, the most famous is JT gravity, which is a theory for gravity and also of a dilaton field. So the kinetic term is in this guy. I just wrote it here as a reminder. And for instance, this is like the usual idea is that this is the no kinetic term for the phi field. You integrate it out, and then this restricts you to consider surfaces of hyperbolic signature. Okay, and one of the major recent developments, for example, in this in a paper a few years ago already by Saad, Schenker, and Stanford, is that they discovered that this theory of 2D quantum gravity is actually dual to a random matrix integral. Or an ensemble, if we interpret the matrix as a Hamiltonian, is an ensemble of quantum system instead of a single one. Okay, so that's sort of like the context in which we'll be thinking about it a little bit. Of course, relation between 2D gravity and matrix integrals goes back a little longer than just the last few years, and this goes to the minimal string. And the basic story about matrix integrals is that you have this. So a matrix integral is defined as the following integral. So I wrote down the partition function here, and you integrate over matrix H and n by n matrix, subject to some potential. Okay, and what is relevant to this string theory duals, for instance, in the minimal string, is is a particular large n limit. Okay, so and large limit is it turns out you can solve this matrix models through various techniques, which might or might not be familiar with. We're talking about polynomials, loop equations, and so on. But the thing that is dual to string theory is something called the double scaling limit, in which you take n, strictly speaking, to infinity, but still zoom in on the edge of the distribution of these eigenvalues, where the eigenvalues are just the eigenvalues of the matrix once we diagonalize the matrix H. Okay, and you do so as in retaining a well-defined density of states. This is a little bit of a song and dance, but the main point to remember is that in the relevant double scaling limit, most of the observables are just determined by this leading density of states. So in this this limit, observables admit a genus expansion. So for example, one type of observables that people like to talk about is correlation functions of partition functions, or in other words, trace over the thermal partition functions, trace over e to the beta times the original Hamiltonian. And turns out that in this double scaling limit, they admit a genus expansion, very much like the string theory expansion in G string. And the sort of the magic or the simplicity of matrix integrals is that all this genus, all the coefficients of this genus expansion, of the partition functions, are actually entirely fixed by the leading density of states rho e. So the main point is that as soon as you give me a density of states for your particular matrix model, you can, in principle, using various techniques like topological recursion, you can compute any sort of higher genus observables in this type of matrix models. Okay, we'll come back to this in a bit more detail, but that's the main upshot. The matrix integrals are solvable, and in this particular double scaling limit, there's a connection with string theory in a genus expansion sense. Okay, so let me flash you the main result that we're gonna see today, at least one of them. In some sense, you can see a result as of providing a stringy realization of this JT gravity matrix model duality, but now we'll phrase it in terms of string theory. Okay, so to phrase it slightly more concretely in terms of the ingredients of the previous slide, so the Virasoro minimal string, which is the worldsheet that I described a couple of slides ago, the claim is that this is equivalently described by a matrix integral, double scale matrix integral, whose density of state is given by this. Here, sinh 2 pi b root e, sinh 2 pi b inverse root e over root e. And this comes in a family, the family parameterized by this parameter b in red that I'll describe what it means slightly more precisely in the next slide, in the next few slides. But it's a whole family. Root b can be any real number from 0 to 1, for example. And in a particular limit, as b goes to 0, in some sense a semi-classical limit, it reduces to the JT gravity matrix model duality of Sat, Schenker, and Stanford. As you can see, for instance, if you take the limit of b going to 0 in one of these cinches on the blue box, it linearizes and you get back just the sinh root e of JT gravity. Okay, so that's one of the main claims. But you'll see that the way we phrase this duality will be a little different. It will be more stringy than the path integral derivation of JT gravity. Okay, so here's just a slightly more detailed sort of set of results of what we did. So we'll start with perhaps the most direct description of this new family of theories, which is the worldsheet CFT, the string theory side of things, with the ingredients I mentioned above, timelike Liouville CFT and spacelike Liouville CFT. We'll see that this makes a little bit more precise a particular JT-like theory, sinh dilaton gravity. we'll see that. And the duality with the matrix integral on the right-hand side, we'll see that there's a little bit of a nice connection with sort of a slightly different version of pure 3D gravity. This will be sort of the connection point between these two dual pictures. And I'll try to describe this a little briefly, because I think this 3D gravity piece is, for example, one thing that did not appear in the JT gravity matrix integral duality. So I think this is also slightly new and worth discussing briefly. But okay, so this is the main summary slide.
Just briefly, I've got a really dumb question.
Yeah, please.
How should I think about the 3D gravity in terms of those two? Well, I guess a two-dimensional world sheet and a one-dimensional or zero-dimensional matrix integral. Should I think about that?
Yeah, I think that's basically right. So you can think about this. The worldsheet theory lives on this sigma. This.
So you do something like a Kaluza-Klein reduction of the 3D gravity to get that. Okay, then how do you get to the matrix integral? Oh, that must be some sort of zero mode restriction.
Very roughly speaking, it's a bit convoluted because there's a very non-trivial mapping. More or less, partition functions of this 3D gravity. So as a preview, partition functions, this 3D gravity can be computed by some machinery of intersection theory and moduli space that we'll get to. But the main point is that they obey some very nice recursion relations. In those, you can directly map to the perhaps more familiar recursion relations of a matrix integral. So actually, it's not very transparent. It's just like it's a map between recursion relations between the observables. But at least it gives you the precise, there's a precise, if you have one, then you go to the other, just mathematically.
Okay. Sounds good. Thanks.
Okay, so let's get into it. So the first and the most direct description, the thing that string theories we're slightly more familiar with. So the worldsheet description. One last thing, one last piece of motivation. So I said that there's some connection to a particular type of JT gravity theory. That theory is this one. So this is the JT potential as well, subject to some non-trivial potential for the dilaton field. The JT gravity case it would just be linear. But the one relevant for our model is a cinch type of potential. So cinch dilaton gravity, sometimes called. So it's a cinch phi potential. I guess maybe I should note that some classes of deformations have been studied in the JT literature recently, notably by Witten and Maxfield and Turiachi as well. And this lies outside that class of theories they consider. Okay, but sort of the main connection to the worldsheet that I will be describing soon is that you can make at the classical level of the action, you can make a field redefinition, noted here at the bottom of the page, going from variables from the Weil factor of the metric to the metric and the dilaton to some other fields, chi and phi, in this particular way. Okay, you plug it in. And you get two decoupled actions, which are here. And for those who've seen the Liouville action before, this is what they are. The first one is the so-called space-like Liouville theory. Perhaps Liouville has a linear dilaton piece, and then the exponential Liouville potential. And the second one has the wrong kinetic sign. A kinetic term sign. So that's why it's called timelike in the literature. But very similar looking, also an exponential potential and so on. Okay, so that's at the level of the classical actions. Now, the sort of the main point of what we're going to do next and how we actually study this theory in practice is that we won't use these classical actions at all, but instead we'll use the full power of conformal field theory in the sense that these are bootstrap solutions to the CFT consistency conditions.
Before you go on,
yeah.
Sorry, let me ask another stupid question.
Oh, yeah, of course.
The wrong sign term, what you call the timelike Liouville term, why shouldn't I be worried about that sign?
Yeah, so let me give you two answers. Let me first give you even though we're not discussing the target spacetime, but just to make you feel more comfortable, this is what we actually do for bosonic string theory, for example. We flip the sign of the time-like free boson.
Okay, fair enough. Fair enough. Yeah. Yeah.
The answer in that is that like we actually don't care too much about the CFT because that's sort of like an auxiliary thing. What we care about is the target spacetime. But yeah, the other point is yes, it is true that this theory will not be unitary in the usual sense, but it will only be mildly non-unitary in a sense that we'll come back to soon. So it won't pose a problem.
Okay. Okay. Okay.
And I'll tell you I'll tell you how it's non-unitary and how it's okay.
Okay, sounds great.
Yeah, but again, the sort of the main point to emphasize is that we won't be using the classical action. We'll be using CFT techniques instead.
Okay.
Alrighty. All right. So back again. So this is the worldsheet theory in terms of CFT. So time like Liouville CFT and space like Liouville CFT, whose actions from the previous slide. Okay, and to put it into context, just if you replay this weird, perhaps weird ingredient, time like Liouville CFT, with a minimal model, this is what we usually call minimal string theory. If you replace it with just a free boson, a time like free boson, which we were just talking about, this would be C equal to 1 string theory. So for those who knows what these other theories are, then we're just doing a simple modification of that. With time like Liouville CFT. Okay, but let's describe this a little bit more detail, what these are, what these ingredients are, one by one. So let's start with this blue one, which is slightly more conventional. It's a unitary CFT and so on. The kinetic sign of that action was the correct one, the positive one. Okay, but in terms of CFT, it's labeled by this following parameters. So the central charge is labeled like this: 1 + 6b + b inverse squared. This is the b parameter that we'll be talking about. It's a label for the central charge, some real number from 0 to 1. Okay, and is the b is also the number that appears in the exponential potential of the field in the action, but it's some number that parameterizes the central charge. Okay, so
sorry, I keep asking dumb questions. How essential is the non-compactness, just out of curiosity? This is going to be some minimal model. I guess you're stuck with whatever it is. Okay, sorry, I think I've answered my own question. I just saw that non-compactness and thought to myself, gee, why can't they just take it to be I don't know, a 25 torus or something like that? But
yeah. I mean, yeah. So it's like, of course, in bosonic string, what we do is we take free bosons, but in this case, we take a slightly more interesting ingredient.
Okay.
But it's still non-compact in the sense that it's like you can interpret it as full dimension in space.
Okay, fair enough.
Okay, that's what non-compact means. It's just that it's a real value field on the entire line. Okay, so the first piece of data to be specified in this CFT is just what are the list of operators. And let me denote them abstractly as VP, labeled by some P, which is usually called the Liouville momentum, and it's just a real number. The conformal weights are given by this C minus 1/24 plus P squared. So in this case, C is always bigger than 25. So this H and H bars are always positive. So okay, very good. We're a unitary CFT. And then the second piece of data is how this interact with each other. So the 3-point coefficients pictorially in this 3-point function. The main upshot is that it's a little bit of a complicated formula, but it's very explicit. It's the so-called DOCC formula. And it can be written in terms of some cousins of the gamma function, but if I write it down, probably wouldn't be too illuminating. So The main point is just that it's some explicit function. Okay, so at least in principle, in terms of the CFT bootstrap, this is all the data you need to know to completely specify the conformal field theory. So for example, at least in principle, with these ingredients, you can compute any higher point function, even in any genus surface, with genus, higher genus than the sphere, for example. Okay, so that's what this is. Now let's see how this first ingredient, the timelike CFT, is a little bit different. So naively, you start with the same ingredients as this same parameter b, but you want to go into the regime such that the central charge is less than 1. Okay, so totally naively, what you want to do is take this parameter b and take it to some imaginary value. That's because you get a minus sign in front of the 6, and you're subtracting from 1. Okay, so that's what morally you have to do. So one thing you can try is just all this complicated DOCC formula, you can try to continue to this imaginary value. And the upshot of that is that it doesn't work. So the analytic continuation precisely fails precisely at these values. This is purely imaginary values. Okay, but there's another solution to the bootstrap equations at this branch. It's very similar looking, but it's slightly different. So again, it's also non-compact conformal theory, but it'll be non-unitary. And let me tell you how, for example. So again, the first piece of data is the operator spectrum. So let me call it V hat, and the hat will be just to denote this other timelike Liouville CFT, to not confuse them with the others Liouville CFT. And the conformal weights are given by the C minus 1 over 24 plus P squared, where P hat is also a Liouville momentum, some real number. Okay, so now, if C is less than or equal to 1, which is relevant for this regime, then the conformal weights can be negative. So that it is non-unitary, for example, in this sense. The conformal weights can be a little bit negative. They're still bounded from below, which perhaps saves you a little bit of trouble from what Eric was perhaps worried about. So they can be negative, and that's non-unitary, but they're bounded at least. So that's still okay. And the second piece of data, of course, is like the 3-point functions, the dynamics of these operators. And it's also known. And in fact, if you choose some nice convention for your vertex operators, you can arrange it so that actually its 3-point function is just the inverse of the original DOCC formula. So it's just 1 over the previous one. So that's kind of a nice feature of this timelike Liouville CFT. Okay, but in particular, it's distinct. It's not the same formula. It's 1 over that formula. Okay, but it's also known and very explicit. Okay, so we've described this sort of 2 ingredients. Now the next step to think about the string is just to build so-called physical states or on-shell vertex operators out of these ingredients. And let me denote them by curly V here. And it's just made up of the 2 vertex operators that we described, VP and the other V hat P. And of course, the condition for it to be on shell is that it has to be equal to 1, the sum of them, of their conformal weights. And so then this specifies the P hat to be the imaginary of the P of the other Liouville. Okay. I won't have time to go into this, but I guess I'll just state that doing this continuation of the P hat, I told you they were real originally, but now you have to continue them to imaginary. This is harmless, turns out. No poles cross any contour or funny things. So that's why this timelike Liouville theory is nice, because doing this continuation is actually very easy. Very trivial, like nothing interesting happens, and you can just safely do it. If you try to do something like that with the other Liouville, then it would be much more complicated. But okay, so that's
so just to clarify, just so I understand, the C greater than equal to 25 and the C at less than one piece is just essentially look formally like analytic continuations of one another. They're very closely tied in that particular sense. They're not completely independent theories. They're, I guess analytic continuation isn't quite the right word, but they're formally analytic continuations of one another.
Yeah, they're definitely related. One instance of that is that the 3-point functions are inverses of each other. But I guess I do want to emphasize that they're not analytic continuations of each other. So you cannot get from one to the other by, for example, continuation in this parameter B.
Okay.
Yeah. So you can continue in B from the usual space-like one. And it makes sense almost everywhere in the complex B plane, except this purely imaginary branch. But then again, there's another solution, and it's closely related, and it's also known. It's very explicit. But you're right that they're very related, as you'll see in a second.
Okay. Okay. Thanks.
Yeah. Okay, so that is the main theory to be discussed, and of course the observables that one wishes to compute are like the analog of scattering amplitudes. So just compute correlators in these two ingredients, the timelike and the spacelike Liouville CFTs. You compute this, and then you integrate over a moduli space of the given Riemann surface, and that computes for you the string scattering amplitude. However, let me draw it like this instead, as in the figure here. Usually, how we think about it is like a punctured Riemann surface, where the punctures are supposed to represent the closed strings that come in and then go out. That's the scattering amplitude. It's kind of like a flat Feynman diagram. But in this case, let me draw it suggestively like this. Instead of a puncture, I'll draw it as a red circle, representing a geodesic length, if you want. This is more in line with the JT gravity discussion, that really the observables are just the partition functions with an appropriate assigned length are these. And what the JT gravity path integral computes in that sense is just the area of this 2D surface. So in this case, of course, we're not doing any path integral. We're just doing this string theory computation. But the interpretation will be the same, that this integral, this string scattering amplitude, will compute the volume of this, or area, I guess, surface area, of this 2D surface, where the length of the geodesic boundaries in red are given by this external momenta P. So what I'm saying is that instead of interpreting P as the momentum of the closed strings, for the first part of the talk, we will just actually interpret them as lengths of this 2D surfaces. That's an interpretation. Of course, the computation is the usual thing in string theory. Okay. Okay. So
actually, before you go on, sorry, I keep interrupting. I apologize. I'm just curious about
this is better. Yeah.
See, it's absolutely convergent. Just to clarify that I understand what you're saying. Ordinarily, in integrals of this form, there are poles at the corners of the moduli space, essentially, or there are issues at the corners of the moduli space. So in particular, you're saying it's not just absolutely convergent over the interior. You really mean all the way at the boundaries. It's well behaved. Okay.
Yeah, exactly.
Okay, great. Please continue. That's I just wanted to make certain I understood.
Yeah, exactly. So this is in some sense a little nicer, right? Because in the other string theories, as you mentioned, there's typically have to worry about the generation limits of moduli space, and usually it's not a problem. We just analytically can continue from where the integral is defined, and we get some. That's how we get the Virasoro, Shapiro, etc. In this case, we don't have to do that. It's just manifestly convergent, so it's actually kind of nice.
Okay.
Okay.
Great.
So that was this was meant for a comment. For the experts, I guess, who like thinking about these integrals. Yeah. Okay. Cool. Okay. The simplest example in which you actually don't have to do an integral is just a 3-point function. the modular space is empty. It's just so in this case, it literally reduces to the product of the 3-point functions of the underlying ingredients, time like Liouville CFT and space like Liouville CFT. And well, as I told you, the structure constants are inverse of each other in a nice convention. So then they just cancel out at this level. So then it's just one. So this is the simplest thing. Of course, you can view this as just my choice of convention. You can arrange it so that it is one. It is non-trivial that you can arrange it in this way, but okay. So the simplest example, but for example, a lot more non-trivial would be the 4-point function. And of course, I won't describe how to do this in practice, but it's a somewhat straightforward computation in conformal field theory. And let me just give you the cartoon of what would this entail, just so you know that it's not as simple as the previous one. So you have to compute a 4-point function in Liouville theory, and each Liouville theory. And that you decompose into the ingredients that I told you about, the 3-point functions, as in this cartoon on the right-hand side, where you decompose into two 3-point functions and then integrate over the intermediate momentum P. Okay, so you got two factors of the DOCC formula, multiplying a conformal block, Virasoro conformal block, which are complicated functions. In fact, we don't even know a formula for these, but we do know some recursion relations for those. Then you're supposed to integrate it over the intermediate state. And finally, you have to integrate over the moduli space, the position of one of these vertex operators. It's kind of a nasty thing to do. But, well, you can do it. And the surprise is that, well, for example, you can do it numerically. And the surprise is that it takes, here are some plots just to show you that, one can actually do it in practice. But skipping this, the main point is that at the end of the day, you get something like that looks just ridiculously simple. It's just some polynomial in the piece, in the length P. Here's another one you can more or less do kind of easily, not so much more complicated, the one loop, 1 point. And it also takes a very simple p-squared dependence. Okay, so this is kind of nuts. Like this DOCC formula of conformal blocks are like very complicated functions. And somehow at the end, it reduces to something simple. So this is sort of like a very serious hint that there's a much better description of this theory that ought to be there, at least. Okay. All right. Let me also point out that in the sense of string theory, you can already tell that this is not like a conventional S matrix element. There's no poles or discontinuities that one would expect of S matrices. These are just polynomials, so it's even simpler than usual string theory. Okay. All right. So we described the first piece of this sort of diagram in its most direct, but perhaps nastier description, the worldsheet CFT. Now let's take a brief detour to talk about this 3D gravity, which again, yes, we can think about it as some dimensional reduction of the theory of the 2D worldsheet. All right. And for this, we'll use some recent work, well, some work that goes back to the work of Hermann Berlinde back in the day, in which they were studying 3D gravity on a general 3 manifold. And the proposal was that, well, of course, if you want to quantize 3D gravity, you have to pick a time slice, which, for instance, we pick it to be a Riemann surface. And then the very first question that you try to answer when you're trying to quantize a theory is like, okay, what is the phase space? Once you find the phase space in a form, you want to associate a Hilbert space to quantize it. The main claim of Berlinde back in the day, even as early as the 90s, I think, his paper was, is that the claim is that for this particular type of topologies, Riemann surface times S1, at least, the Hilbert space can be associated with the space of conformal blocks. So that's the claim. One can try to derive that, and that turns out to be correct. But then that's not the end point. This is just sort of your starting point. Okay, what's the Hilbert space? Your next step in the quantization of your quantum mechanical theory is like, okay, what is the inner product in this Hilbert space? And this was made slightly more precisely by the work of Collier, Eberhard, and Cheng last year. And they defined the following inner product between states in this Virasoro TQFT Hilbert space, which are just conformal blocks. Okay, so you take two conformal blocks, and what the prescription is that you multiply them together, multiply by, from this point of view, something auxiliary, timelike Liouville CFT correlator, just so that the total center of charge cancels together with the BC ghost. But crucially, you have to integrate not over moduli space, but something about something called Teichmuller space. The reason for that is that the multiplication of these two blocks is not a correlation function; it's just a piece of it. So it is not crossing symmetric on its own. So it wouldn't make sense to integrate just over moduli space, but you have to integrate over the full Teichmuller space. So just to as a reminder, for instance, the torus 1-point function, just to keep some concrete example in mind, the moduli space is this keyhole region, the fundamental domain that kind of looks like a keyhole. Teichmuller space associated with the Teichmuller space of the torus 1-point would be the entire upper half plane. So just like the copies of the keyhole region. Okay, so the claim is that you're supposed to integrate over that full complex plane rather than the fundamental domain for this inner product. Okay, but the main point is that this looks very close to the computation we were trying to do in the string theory. Not quite because of tiny details like Teichmuller instead of moduli space and a single conformal block instead of a full correlation function, but it's almost there. Okay, and then the main point is that we were able to massage it, at least formally, to something that is closer to this string theory amplitude. So perhaps it's not super important, but the main claim, which is supposed to be summarized in this equalities, is that if you evaluate now the partition function on this Riemann surface times S1, the 3D drive partition function, which by that I mean just evaluate the trace over all the states in the Hilbert space, which I told you is supposed to be Virasoro conformal blocks. Okay, the couple of lines of algebra, the main point is that you can massage it to be precisely that string theory amplitude. Okay, so this is only useful if one is easier. So for example, I showed you a couple of slides ago that computing string theory amplitudes is hard. So the right-hand side is hard. So this is only useful if there's a better way to compute these things. Partition functions of 3D gravity in this particular type of topology. Okay. So if this was too quick, I mean that's the main option. So that there is a better way, and this is where we draw some heavy machinery of algebraic geometry, which is a very well developed subject on how to compute this type of one step before that. This is gravity partition functions in a paper by Lawrence Eberhard a few years ago already. He mapped it to some problem in evaluating the integral of the moduli space of some cohomology classes, appropriate ones. The main point is that these are sort of standard cohomology classes on the moduli space, and there's very well developed machinery to compute these this intersection numbers. So then we just borrow that machinery to actually compute this partition functions, which we saw is the same as the string theory amplitudes we started with. Okay, so that's the main upshot of this brief detour. But at least formally, we can map the problem of string amplitudes to to something that has a well-developed technology in intersection theory. And then, right. One thing that's a bit more physical, so going back to a little bit more physical, is one thing we can do fairly easily, just from this 3D gravity perspective, is to evaluate what is the disk amplitude. Even though we have not talked about boundary conditions yet, we can already kind of see what it has to be from this 3D perspective. So if we take this picture, for instance, in this hand-drawn picture of the topology of the disks shaded in yellow, times S1, so it's just a solid torus. And by ADS3 CFT2 correspondence, we know that this on the boundary corresponds to just a vacuum character, just like Maloney and Wheaton type of story. So, for instance, just dimensionally reducing to the picture, we can write down the disk partition function just to be proportional to this vacuum character, just from this dimensional reduction picture. Similarly, we can derive the trumpet. So it's like a cylinder diagram, but more commonly referred to as trumpets in the JT gravity literature. It's also a 2D CFT character, but the non-degenerate one, associated with some momentum p, where the p is this geodesic boundary. Okay, and this just comes from knowing the 3D picture, without getting too much into the without even getting into any intersection theory. Okay, so yeah, and so those are the last two pieces that one can then just describe the partition functions that we maybe began the talk by discussing the main observables in the matrix integral, which is just correlation functions, is trace beta h. We can just get them by gluing to our volumes, the string theory amplitudes, if you want, glue in the trumpets by integrating over this momentum p in red, and then we get the partition functions. So we get the full ingredient. So we already discussed how to, at least in principle, compute these volumes, and then we saw what the trumpet is, and then you can start gluing all these observables and get, if you like thinking about partition functions, you can compute these partition functions. Okay, but this might have been a bit quick, but the main upshot is that now we can readily, in some form, either derive or guess what the matrix integral description is. And the density of states is this that I started with. And let me say a couple of comments about this density of states. The first is that for those who like 2D CFT, this is a natural object. This is nothing but the, I guess it's usually called the Cardy formula for 2D CFT. So if you modular transform this, you get just a vacuum character. So this is a density, and if you integrate against a character, then you get the vacuum character. So this is why we call it the Virasoro matrix integral, because this is just the Virasoro, if you want, the Cardy formula for 2D CFT, which has the Virasoro symmetry. Okay. And again, if you take the limit going to b going to 0, you get the JT, just a single cinch density states. Yeah. And of course, and then you can, well, before I phrased it in terms of partition functions, but if you're more familiar with matrix integrals, perhaps a quantity you're more familiar with are resolvents, which can also be readily computed and also admit a topological expansion, just like the ones that we were talking about. And once I give you the density of states, you can invoke this machinery of topological recursion, of Einard and etc. to compute this type of observables. And again, by doing the Laplace transform, you can either go from the resolvent to the partition functions that we described earlier. Okay, so here's just kind of little bit of a summary of what are the observables. You can pick your favorite. For instance, if you like thinking about string theory, you can just think about the volumes or the string amplitudes on one side. You glue the trumpets, which the trumpets were just the non-degenerate characters, and then you get the partition functions. If you like JT gravity, this is probably a more natural observable. Or if you're more familiar with matrix models, you might want to perhaps are more comfortable talking about resolvents. So you can also choose that to discuss. And you can go from one to the other just by doing a simple Laplace transform. And the Laplace transforms are pretty easy because these are just polynomials. So there's no subtleties and contours or anything. It's a simple transformation. Okay, so for instance, let's talk about, again, let's go back to the string picture, which at least that's the one that I personally like the most, the volumes. And the topological recursion that I was alluding to throughout, from this perspective on the volumes or string amplitudes, it takes this form. Perhaps not super illuminated to just stare too much, but it's just something explicit. And as usual, it's just this topological recursion is just you start gluing 3-point functions into other previous steps in the recursion in several different topological ways, as in these pictures, and then you get a higher point function. And this once you have the 4-point function, you plug it in again, you can build a 5-point and so on. So once you have the 3-point and this kernel, which is the thing that you're supposed to integrate with, which is given explicitly here, and which you can derive, for instance, from the density states that I gave you. Not surprising, is a product of signs and cinches. Sure. Then this you can compute in any of the string amplitudes that you want fairly quickly. So just to give you an example, again, we saw that this example, the 4-point function, was already a little bit complicated, even though it reduced to this simple polynomial. But just to show you, using the recursion of the previous slide, you can code it in Mathematica if you want, and you can get, for instance, something more complicated, like this genus 2 frequent function, and it kind of looks like this. Okay, and you plug in code in Mathematica, you get some answer. And of course, you can go nuts with this amplitudes. But the main upshot is that this string theory is dual to this matrix integral. I won't have time to describe this in detail, but you can also match non-perturbative effects on top of the perturbative expansion in the genus expansion. These are from the string theory side. These are so-called CC instantons. And they involve also some diagrammatics, like the one picture at the bottom. But I guess in the interest of time, I think I'll skip this and just say that those can also, at least the leading order ones, can be matched as well. Okay, so that this provides some class of non-perturbative evidence as well for the duality. Okay, so that was the worldsheet. That was the quantum gravity story. Partition functions, volumes, etc., and duality with matrix integral. So let me spend the last 5 minutes discussing something that perhaps the string theories were a little bit more more used to. So okay, what is the spacetime? And well, when I ended with this, because I think this is still an open question. But I think it can also lead to a nice story. Okay, so what is it? So part 2, it will be asking what this piece is. Okay, but for that, I'll have to take a brief interlude just to remind you what 2D string theory is, because that's where the most of the intuition will come from. Okay, so 2D string theory, or C=1 string theory, has this similar looking ingredients, but instead of having the timelike Liouville CFT, we just have a free boson, which represents time. Okay. Yes. Okay. So, and again, this is, for instance, these are supposed the on-shell states. which are required to be 1, 1, are just massless scalars in space-time. Mostly because the condition that the weight has to add up to 1 leads you with some massless dispersion relation. Typically, in the bosonic string or something, this is something negative, so that's why we call them tachyons. So something with a negative mass, but actually in this two-dimensional string, these are actually massless scalars. Okay, but the main point of how do we think about this in space-time? So let me to draw a picture. Let me write down the field that is interpreted as space, which is the space-like Liouville field. So here's the action again. Okay, so in kinetic term, and then the two main ingredients. The first is a linear dilaton piece, multiplying the field phi. And if you remember for string theory, the dilaton is what determines the strength of the string coupling. So on one hand, on the one side of space, so this is space, this line is space. When phi is very large, we have very strong coupling. And in the other regime, we have very weak coupling, when phi is large and negative. Okay. But then comes the purpose of this second term. This potential, exponential potential, what it does is shields this potentially uncontrolled region of spacetime. Okay, so then there's no trouble. And the massless scalars that I told you, what would be tachyons in higher dimensional string theory, are just plane waves that come in here, interact somewhere here in the middle where the string coupling is non-vanishing, bounce off this Liouville wall, this exponential potential, and then go back to here, the asymptotic region of weak coupling. So this is what happens in spacetime in 2D strings. Here's another picture of both space and time. The gray region is supposed to represent the Liouville exponential potential. So you have one closed string coming in, bounces off the wall, and then two outgoing strings in this direction. And this theory, for example, does have an S matrix, more conventional S matrix, which, for example, you can view here, some delta function conserving energy, and slightly more interesting piece with imaginary pieces, which you can view from factorization and so on. So it's a bit more conventional. Okay, but now what is the one that it was started with? Once we, instead of a free boson, as in the previous picture, we replace it with time-like Liouville CFT. So what does it mean in spacetime? So let's see if we can try to draw the same picture. This is, again, reminding you of the on-chill states, and reminding you that we had to continue the time-like Liouville energy to imaginary values. Here now it's more natural to why we did this continuation to imaginary values, because the omega now has interpretation as an energy. Because then the dispersion relation with this minus sign is a Lorentzian massless dispersion relation. But what is the target spacetime? So what does it look like, the picture of scattering? So for that, let me go back to the Liouville action with the two terms. Okay. But now we want to do the time-like one. So the first step is to, as we saw, continue the parameter b to purely imaginary values. For simplicity, let me consider the b equal to 1 limit, just for simplicity. So the first term just vanishes, and then we have this potential with an imaginary value. But then the second step is to do a Wick rotation in field space, just like we do in string theory, so that we get the kinetic term, and we can interpret this as a time direction. But now the potential gets this form. So it's again real. But now remember that this chi-naught now is interpreted as the target spacetime time direction. So now this is a time-dependent potential in red. Okay, so how does it look like? So again, we have our space and time. The gray area still represents the same space-like potential, the wall, which is the same as in the previous model. But now we have in blue the time-dependent potential. So in the infinite past, it grows really big. And in the infinite future, it decays. So there's no potential in the infinite future. So then the observables are a bit different. It's not an S matrix because there's no in states. There's only out states. So in other words, we only have closed strings going into the future. So a better way to think about it is we have the way to think about it is that we have some initial state of the universe. I put it here in quotes, the Big Bang. And we are able to see from the perspective of asymptotic observers here, just the usual closed strings that radiate from this time-dependent potential. Okay, I think I'll skip the combinatorics, but the main point is that from the perspective of an observer in the infinite future, you can try to reconstruct what this wave function is by computing the string amplitudes. The main point is that instead of computing an S matrix element, what you compute are components of this wave function, of this initial wave function. For instance, you can see perhaps a familiar squeeze state here from time-dependent quantum field theory, plus corrections in G string that you would compute by this scattering amplitudes. Okay, so this is the summary slide coming to an end. In the first part of the talk, we described this new duality between this Virasoro minimal string, viewing it as a model for quantum gravity on the worldsheet, and we saw that it was dual to a matrix integral. On the other hand, from the spacetime point of view, we gave at least an interpretation of this as a cosmological background with this time-dependent potential in blue. And the question now that I would like to pose is that whether this, just like other two-dimensional string theories, the question is whether it has a matrix quantum mechanical dual, so a full quantum mechanics, which in particular has time. So I think it would be a very nice question to understand whether, in this model at least, we can try to understand whether there's some sort of emergent time in this dualities. But let me so with that, let me end here with some questions. Thank you.
Thank you. That was a very nice talk.
Thanks. Any questions?
We've already asked a bunch during the talk, so it's
Yeah,
thank you for the questions. They were great.
Yeah, Victor. So the 2D minimal string theory, as you said, it's like dual to the matrix model there. Is that matrix model also an ensemble averaging, or it's some certain matrix model?
Yeah, you can interpret it in that way. So the matrix of the matrix integral, it's, you can interpret that as being some Hamiltonian of some quantum system. In at least the work that I presented, strictly speaking, we didn't give that precise interpretation because we didn't tell you what that quantum mechanical theory is. In the JT gravity case, well, it's supposed to be the Schwarzian. So at least there is something that has a nice interpretation as a quantum mechanics. Yeah. That piece of the story we still don't know for sure what, but it should be some sort of deformation of the Schwarzian. So I would say that yeah, the interpretation it is still that it is an ensemble of Hamiltonians.
Yes. And and also in your context, you have this 3D gravity. Is that 3D gravity a holographic theory?
In this sense, yes, but it's kind of simple. It's since it's 3D gravity with a negative cosmological constant, so it's also of the ADS type.
Yeah.
So yeah, it's supposed to be it's supposed to be dual to some 2D CFT that lives at the boundary of that 3D surface.
But that's
not the same CFT that is describing the Virasoro.
Yeah, right. Okay, great. Okay, great.
We didn't really use that much. We just used one basic fact that just empty ADS or thermal ADS is, for example, supposed to describe in terms of the asymptotic CFT2 in terms of like just a vacuum Virasoro character. But that's sort of generic for any ADS3 CFT2 duality.
I see.
Yeah.
Yeah, thanks.
Mm-hmm. Mm-hmm.
Any other question? Yeah, if no, let's, yeah, you have.
No, I just.
Oh, okay. Yeah, if no, let's thank Victor again.
Oh, thank you so much.
Let me stop.